Welcome back to section 6.2, angle and orthogonality in an inner product space. And we were talking about our row space and our null space, and we showed that they were orthogonal. We even drew a picture here. Let me share that screen with you. So in the plane was our blue and orange row space vectors, and the purple was our null space vector. It was not in the plane. And we saw that together they, so if I don't have the purple vector, I can only make a plane. If I do have just the purple vector, I can make a line, and neither one of those covers all of three-dimensional space. But if I use both the plane and the line together, the row space and the null space, I can make anybody I want. So for example, if let me take out the blue and orange vector, otherwise it's going to get really cluttered here really fast. If I wanted to make the vector -1, 4, okay, remember that the purple vector stood for our null space vector, and -1, 4 is this red vector. What I need to do is find a vector in the plane. So you can see that in the plane, and then I would add something that's a scalar multiple of the null space vector, and I could make any vector in the three-dimensional space. So you can hopefully see how that works there. That's why we call the row space and the null space orthogonal complements, because they complete each other. Moving back to our paper here, if we have W is any subspace of some vector space V, then there's another subspace, we read this as W perp of V, that completes V, meaning that any other vector in W and any vector in W2 are going to be orthogonal to each other. And furthermore, any vector, kind of like our P vector, which I just made up for me, was -1, 0, 4, calculator randomly picked that, would be equal to, if I were to do this guy right here, so we get this guy right here is in W, so let me call him W1, and this guy, the red guy, is in W2, or the null space, but he's orthogonal to anything in the plane here. And this W1 vector coming from these two, this linear combination of our row space vectors, turns out to be 1, 1, 3. And if I add to that vector W2, which is in the null space, which fortunately for us, it came out to be 1 times that. So it was just one of our null space vector. And when we add those, we got our desired vector. Okay, so that's what we mean when we say that they complete each other. So something in the W space plus something in the W perp space, the orthogonal complement, together makes anybody in the entire space. And so again, notice that anything in W is orthogonal to what's in W perp. -2 minus 1 is -3, plus 3 is 0. So that's why we call these orthogonal complements to each other. Now W and W perp have a couple more properties. So just to remind ourselves that the only vector in common between W and W perp is the 0 vector. Okay, think of our plane for the row space and our line for the null space. The only vector that was in common between these guys was the 0 vector. Okay, and so that's true. Now, it shouldn't be too surprising, but if I do the orthogonal complement of the orthogonal complement, I get back to my original space. So if I find out what's orthogonal to this plane, it's going to be this line. And then if I find out what's orthogonal to this line, it'll be back to the plane. And if we take a look at this guy, the dimension of the space, the subspace W, plus the dimension of W perp will be equal to n, the dimension of the overall vector space. Okay, so the dimension of our plane was 2, because it had 2 basis vectors. The dimension of our line that was the row space, or sorry, the null space, that was orthogonal to our row space was 1, and 2 plus 1 equals 3, which was the total dimension for the 3-dimensional space that we had there. Okay. So now I want you to try a problem here, but let's kick it up to 4-dimensional space. Okay, we can extend this further. It's just going to be a lot harder to visualize. So if we let S be the vector U1, 0, 1, 2, 4, U2 is 1, 0, negative 2, 3, U3 is 1, 1, 0, 1, and U4 is 4, 3, negative 2, 0. This is living in 4-dimensional space, but we want to see what we can cover with those vectors, those 4 vectors. It could possibly be, since there's 4 of them, all of 4-dimensional space, but it might not be. So we want to find the span of these 4 vectors. So let's see what we could make with them. And then let's find a basis for W. So to do that, let's check C1 times U1 plus C2 times U2 plus C3 times U3 plus C4 times U4. Okay. And let's see, first off, since we need to do a basis, let's check to see if they're linearly independent. So let's do our definition of linear independence and set those equal to 0. That's going to set up a system. Oops, that's a 1, 0, negative 2, negative 3, 1, 1, 0, 1, 4, 3, negative 2, and 0. And if we RREF that matrix, I know this has to be zeros, but let's see what we get. We get 1, 0, 1, 3, 0, 1, 1, 4, and then 2 rows of zeros. Uh-oh. So that tells me that the 3rd vector and the 4th vector are scalar multiples or linear combinations of the first 2 vectors. So a basis for W would be our first 2 vectors. So that means W is going to be 2-dimensional, and it will be covered by the vector 0, 1, 2, 4 together with 1, 0, negative 2, negative 3. So that's W, and that's a 2-dimensional subspace in 4-dimensional space. So let's see if we can find W perp. Well, it's what's orthogonal to W. And so we're going to just take the, well, these are the, so let's take our matrix. And if we take our matrix and use our rows in here for our vectors, and if I take and augment by the 0 vector, we know that the row space and the null space are orthogonal complements. So knowing that these vectors would be the rows of my matrix, if I find the null space of that matrix with these as rows, that null space will be a basis for the orthogonal complement. So if we take this guy right here, this matrix, and RREF him, and find his null space, we'll find the orthogonal complement. Let's do that. So if I RREF this matrix made up of the rows, I get 1, 0, negative 2, negative 3, 0, 1, 2, 4. Oh, wow, gee. You can see that that's just a row swap, and now he's in reduced row echelon form. But you can see that we have two non-zero equations in, four unknowns, so we're going to need some parameters. I'll call x4 t and x3 s. Therefore, x2 would be negative 2s minus 4t, and x1 would be 2s plus 3t. So if we were to separate them out by the s and the t parameters, we'd have s times 2, negative 2, 1, 0, plus t times 3, negative 4, 0, 1. So a basis for the orthogonal complement, W perp, would be 2, negative 2, 1, 0, together with 3, negative 4, 0, 1. And you should check that each of the vectors here in W perp is orthogonal to each of the vectors here. And I'll do that. So here's 0, minus 2, plus 2, plus 0. So according to the Euclidean inner product, these are orthogonal. And you can check that every possible pair is orthogonal. So the last thing I want you to do now is to make up a non-trivial vector in R4 and write him as a linear combination of these four vectors from the row space and the null space that together complete all of R4 and make a basis for all of R4. Okay? All right.